Okay, come on. All right, so I think we are now live on YouTube. Okay, so, oh, wait a minute, not yet. Hold on. Okay, so now we're live. All right, so let me go back to assignment number 7. Oh, before I forget, let me say that for assignment number 7, let me go to the Canvas page. For assignment number 7, there are actually 2 links for assignment number 7, and I forgot to mention that. Let me just show you where they are located. So assignment number 7. So there are 2 documents, and I forgot to put them together, and I just realized yesterday. So if you look at here, this is the original assignment 7 that we started working on. And then there's the addendum, right? So make sure that you download that as well and complete it when it is due so that you can get full credit. So both of these is basically assignment number 7. All right, so and we'll be working on this as well, of course, but we're going to continue our discussion on the original assignment number 7, which is this one right here. No, not that one, I'm sorry, that one. And we did number 1, at least some of number 1. And I think I told you guys to try the rest. So before I move on, any questions about any of the parts of assignment number 1? I mean, question number 1, I'm sorry. Any problems you have with question number 1? Any one of the problems I asked you to attempt?
Are you able to hear us? Can you hear anyone speaking?
Oh, I think, hold on. Miss McCoy, were you saying something?
Yeah, a couple of us have spoke already and you don't seem to be responding.
For some reason I can't hear you. I don't know. Can you type what you wanted to say in the chat? Okay, let me see here. Okay, so you have a question on assignment number 6, number 2, and assignment number 7F. Okay, so I take it you're talking about question number 1, the F part, right? For assignment number 7, that is. Okay. All right. So what I'm going to do is, I don't know what's going on with the volume. I don't know if it's from my end. Let me see here. Let me go to files. And you said assignment number 6, assignment number 6, question number 2. Oh, I think we did this one already. For this one, oh, there was no amount in the chart for CCL4. Question number 2D, you said. My bad. Oh, if I remember correctly, was this the one I told you guys to skip? I think I told you guys to skip that question because of that reason. Because there's no information in the tables I provided for you for the entropy for carbon tetrachloride. Oh, I told you guys to skip number 5A. Let me see what 5A is about. Oh, right. You're absolutely right. Okay, well, tell you what. For the D part, all right, what I would do is consult the internet, really, for the value for carbon tetrachloride gas. In fact, let me do that right now. So standard entropy of carbon tetrachloride gas. Let's see what comes up. So according to the NIST webbook, let me see here. Oops, scrolling too fast. Let's see. Okay, so according to NIST, the standard, hold on, that's 1 bar. Okay, we'll go with, oh, you know what? Hold on. Let me try this, Wikipedia. Okay, so here it is. The standard molar entropy of carbon tetrachloride gas is 309.65 joules per mole Kelvin. So you can go ahead, right. Thank you, Miss, who said that? Or who wrote that? Watson, Mr. Watson. Right, so it's 309.65 joules per joules per mole Kelvin. So you can use that value. All right. So I hope that helps you. Now, you said there's another question you had concerning assignment number 7, which is the one that we're working on right now. And you said the F part, presumably for question number 1. So it's basically dealing with balancing this equation. Is this what you're referring to, Ms. McCoy? Okay, very good. All right, so let me go through this. So let me turn on my pen. Okay, so for this question, we go through the same steps as before. Now, this might look a bit confusing, but it's actually the same principles that will apply. So first we separate it into 2 half equations. Now, 1 half equation would contain this, as the reactant, and these 2 as the product, right? So Ag to S, the form Ag plus S, all right? And then the other equation would basically contains what's left. NO3 minus the form NO. All right, and then we basically go through the steps as before. So the next step is that we balance all atoms excepting oxygen and hydrogen, which would mean that for the first half equation, we need to put a 2 here. For the second half equation, we don't need to make any changes to the nitrogen. And then the next step is that we balance all oxygens by adding water to each of them. In the case of the first half equation, that means we don't add any water because there's no oxygens. But in the case of the second half equation, we would add 3 water molecules right here, all right, to balance with the 3 oxygens here. And then the next step is to balance the hydrogens. Again, we have no hydrogens in the first half equation. In the second half equation, we have 6 hydrogens here on the right side. So that means that we add 6 hydrogen ions on the left side. And then the final, well, not the final step, but the next step is to balance the charges. And in this case, what we do is that in the case of the first half equation, we have no charges on the left side. We have 2 plus charges on the right side. So what that means is that we need to add 2 electrons on the right side. For the second half equation, we have a total of 6 minus 1, so that would be plus 5 on this side. We have no charges here on the right side, so that means that we add 5 electrons on the left side of that half equation. And then we need to go to the next step of ensuring that the number of electrons lost and gained are the same. So what that means in this case is that we multiply this half equation by 5. So in which case this will become 5 Ag2S to give 10 Ag plus 5S plus 10 electrons. And then this we multiply by 2 to get 10 electrons plus 6 hydrogen ions plus 6 nitrate. I'm sorry, this should be 12 hydrogen ions plus 6 nitrate ions to give 6 NO plus 18. No, what am I doing? Plus 6. I multiply by 2, right? So this should be 2. I'm messing up this morning. So this should be 2. And then 6 H2O. All right, let me just check to make sure. 10, 12. Okay, so I made a mistake here as well. This should be 2. So this should be 2, and then that is 2, and then that is 6. Okay, so now that we have done that, then the next step is to add these 2 equations together. So electrons will cancel out, and there's nothing else that will cancel out. So the final answer becomes 5 Ag2S plus 12H plus 2 nitrate ions. And then on the right side, you're going to have 10 silver ions plus 5S plus 2 NO plus 6 H2O. And again, as I said before, I would advise you all to do a final check through to make sure everything is balanced. So if you do that, you see that you have 10 silver atoms here, which balances with the 10 over here. We have 5 sulfurs here, and this will be 5. I forgot to put the sulfur here. And then 12 hydrogens here. We have 12 hydrogens here, 2 nitrogens here, 2 nitrogens here. And then as far as the oxygens are concerned, we have 2 times 3, 6. Okay, so the oxygens don't seem to be balanced, which means I made a mistake somewhere. So anybody can point out where I made a mistake. Let me see here. I made a mistake somewhere. I must have, because the oxygens. Oh, the oxygens are balanced. No, wait a minute. 2 NOs. Where did I make a mistake? Where did I make a mistake? Okay, so apparently I made a mistake here. Oh, okay. I made a mistake up here. So I have to go back up. I'm sorry. Let me erase this here. And let me see what I made. Okay. I think I made a mistake with the oxygen count. So let me erase all this here and just start from scratch. All right. So in this case here, I have 3 oxygens here. I have 3 oxygens here, and I have 1 here. So what I should have done is add 2 water molecules here, right? And then this becomes 4 hydrogen ions, and then this becomes 3 electrons here. And then now I would have to multiply. Okay, let me erase what I had here to avoid confusion. So in order to get the electrons equal, I'll multiply, in fact, let me erase this here. In order to get the electrons equal, I would multiply the first equation here by 3 to get 3Ag 2s to give 6Ag plus 3s plus 6 electrons, and then multiply this here by 2 to get 6 electrons plus 8 hydrogen ions plus 2 nitrate to give 2NO plus 4H2O. Okay, so let me erase the bottom part here. So let me just do a quick check to make sure I'm on the right track. 4 hydrogens, 3 oxygens, 1 nitrogen, and the total charge on this side is 0. And then I multiply by 2 to get 6, 8, 2, 2, and 4. Okay, so now we add these two equations together. And what will be left would be 3Ag 2s plus 8H plus 2 nitrates to form 6Ag plus 2NO plus 4H2O, and I almost forgot the 3 sulfurs. Okay, so now that we have the balance equation here, I think. Let's check and make sure. We have 6 silvers here, 6 silvers here. We have 3 sulfurs, 3 sulfurs, 8 hydrogens, 8 hydrogens, 2 nitrogens, 2 nitrogens, and 6 oxygens, 2 plus 4, 6 oxygens. And the charges would be 8 minus 2, so that's plus 6 here. On this side, we have only this, which is plus 6. So that would be the balance equation. Now, if I'm not mistaken, the question says that you're to determine the equation in a basic solution. So what we do next, and I'm going to erase this bottom part here, is that we look at the number of hydrogen ions present in this equation, and we add the same number of hydroxide ions to both sides. Whatever you do to one side, you have to do to the other, right? So these here would combine to give you 8 water molecules. So these 4 water molecules will cancel out 4 of these, leaving behind 4. So let me erase the top part here. So I can write down the final answer above. So the final answer is going to be 3Ag 2s plus 4 water molecules plus 2 nitrates. And then on the product side, you're going to have 6 silver ions plus 2 NO plus 3 sulfur plus 8 hydroxide ions. And that's basically how, that should be the final answer. All right. Okay, any questions? Oh, I see some comments here, which I probably, okay, so, okay, all right, I'll take your suggestion, Miss Monahar. I'm going to log out of Zoom and then get back in so that we can have a better way of communicating, all right? So don't leave. I'll be back. Okay, I'm back. Can somebody just say something just to check that I can hear, if you can hear me?
Hello, hello, hello. Hello.
Okay, I think Miss McCoy is trying to say something, but I still cannot hear. You know what? Let me check something here. Let me check. Oh. I don't know what's going on here. All right, let me try to log out again and get back.
I wonder if his volume's just low.
That's actually what I was just thinking.
Yeah, because it's weird. We can all hear each other, but he can't hear us.
Okay, can somebody do a mic check just to see if I can hear you guys?
Hello, hello, hello.
Okay, I think Alexandra was trying to say something and I still cannot hear. My volume? Oh, okay, hold on. Okay, check again.
Can you hear now?
Okay, good, yes, I can hear. 1 minute. Okay. Okay, glad to solve that problem. So let me go back to my share screen. And somebody had a question. Who was it?
That was me.
Ren, okay, yes. And your question
Okay,
is?
okay, so firstly, from yesterday when I went to the testing center, they didn't have your test two.
They should, because I did send it.
And they did say you sent an email, but every single attachment they opened, none of them actually had the test. They just had the formula sheets.
Okay, I'll have to check and see on that. Okay, when we get to our next break, I'm going to see if I can quickly check and see what's going on here, because I'm quite sure I did send it. So maybe it's my mistake on my end. All right. So yeah, go ahead.
And also I had a question about the assignment.
Which one?
Okay, it's a really simple question. If you did like number 1A, for example,
Assignment number
number
What-
7.
number 7. Okay, so that's this one. Hold on 1 minute. Okay, so which question?
Number 1A,
Oh, number
I
7.
just
I'm sorry, hold on. I chose the wrong one. Number 7 is, let me check and make sure. Okay, number 7. Okay, you were saying what now?
Okay, so my question was, I know that the first step is you break it up into 2 equations.
Mm-hmm.
So when you have HCOOH going to CO2, the oxygens are already balanced, so you don't
Right.
have to add water, right? Can you just add 2 H pluses?
Yes, ma'am.
Oh,
That's
okay,
exactly what you should do,
perfect.
right? Mhm.
And then also for number, I think it's on page 8, so that's part H.
Okay, this one?
Yes,
Whoops.
it doesn't specify if it's acidic or basic. Is it supposed to?
Yeah, just leave it as acidic.
Okay,
Yeah,
sounds good.
I went ahead and did both acidic and
Okay.
basic just in
Yeah.
case on that one.
Yeah, no problem, no problem. Okay, all right. Any other questions before we move on? Any other questions? All right, so let's scroll down to continue with assignment 7. Okay, we're going to scroll down now to question number 2. Now, question number 2 deals with what is called a galvanic cell, and that was covered in the videos that I have posted. So what I'm going to do is just give a brief overview of what a galvanic cell is all about. And this is one of the slides that was covered in the video, and it's also available in Canvas, right? So just to quickly describe what we have here, we have a solution here in this vessel of zinc sulfate. In this vessel, we have a solution of copper 2 sulfate. Excuse me, I'm sorry. All right. And in this vessel, we have a piece of zinc metal dipped in it. In this solution, we have a piece of copper metal dipped in it. All right. These two metals are connected to an external circuit through wires. And we have an instrument here known as a voltmeter. And the voltmeter measures what we call the potential between these two, what we call cells. So this would be a half cell, right? We call this the zinc half cell and the copper half cell, or zinc anode and copper anode. We'll get to copper cathode. We'll get to those terms, what they mean. The voltmeter measures what we call the potential. It basically measures the tendency of an electric current to pass through the external circuit, all right? Now, the voltmeter will register a particular voltage, all right, when the setup takes place. Now, the reason why it registers a voltage is because there's an electric current that passes through the external circuit. And the way, or the reason why that current passes through is because here at the zinc anode, we have oxidation taking place, where the zinc metal is undergoing oxidation, and the electrons that are produced as a result of the oxidation will enter the external circuit, all right? On the other hand, in the case of the copper electrode, reduction will take place, right? Where the electrons coming through the external circuit will basically combine with the copper 2+ ions in the solution to form copper solid. So basically what's going to happen over time is that the mass of the zinc electrode will decrease because the zinc is undergoing oxidation, and the mass of the copper will undergo an increase because the copper 2+ is undergoing reduction to form the copper, which will add to the copper that is already there. All right? And this is what happens in a galvanic cell. It's actually a redox reaction where in one half cell, the zinc will undergo oxidation, and in the other half cell, reduction will take place, right? So therefore, what you need to remember when it comes to this setup is that oxidation will take place at the anode, reduction will take place at the cathode. So if you add this equation to this equation, this would be the net equation, all right? So that's basically what the galvanic cell is all about. And basically, the key thing you need to remember about the galvanic cell is that the reaction, the redox reaction that is taking place is a spontaneous reaction, and the energy that is produced is in the form of electrical energy, which allows a current to flow through the external circuit, all right? One more thing I want to point out before we get to the actual question that we should answer in assignment 7. You'll notice that part of this setup is this salt bridge, right? A salt bridge here is basically some inert material, usually it's agar gel, which is soaked in some ionic compound. In this case, the ionic compound is potassium chloride. Now, this salt bridge is very necessary for the functioning of this cell. And the way this works is that if you think about what happens here in the anode, right? The zinc concentration, the zinc ion concentration would increase, right? And eventually there'll be a buildup of zinc ions, right? So if that happens, eventually the cell will stop working. You'll have the flow of electrons passing through the external circuit will be reduced to 0, all right? Now, in order to maintain electrical neutrality, because you're increasing the amount of positive ions present here, what will happen is that the zinc ions will move into the salt bridge and it will be replaced by the chloride ions, right? And therefore, what that does is basically maintain the electrical neutrality of this, and therefore the current will continue flowing. Something similar will happen here in the case of the copper 2 plus or the copper electrode. What will happen in this case is that the copper 2 plus will be reduced in terms of the concentration. So therefore, in order to replace the reduced positive charge here, the potassium will enter into that solution, and as a result, electrical neutrality will be maintained, and therefore the current will continue to flow through. All right. So that's basically what happens in the case of a galvanic cell, and as stated here, there's a spontaneous redox reaction, which is described by this net equation right here. Now, another thing I want to mention here is that there's a shorthand way of representing all of this here and also all of this here in terms of the galvanic cell. So let me try to show you how that is done. So let me just write it out and then I'll explain what this represents. So we call this the, oh gosh, what do I call it again? Let me see if I have it here. They call this the cell diagram. Okay, they call it the cell diagram. So let me just explain, let me write it down here and then I'll explain what it's all about. So this is a cell diagram for this particular galvanic cell, 2 plus aqueous, and you have to include the concentration, which is 1 molar, and then we have a double line here, and then we have Cu2 plus aqueous, 1 molar, and then we continue with Cu here, right? Okay, so let me explain what this is all about, right? So this here represents the anode, all right? And it basically gives you the composition of the anode, right? However, you have to be careful when writing down this in order. You have to write it down in terms of what is being reacting and what is being produced in the oxidation, which takes place at the anode. So based on this equation here, you can see that zinc is undergoing the oxidation to form zinc 2 plus. So you write the zinc first, you draw a line like this, and then you write zinc 2 plus aqueous, and then you put in parentheses the concentration of the zinc 2 plus ion, which is in this particular case 1 molar, right? And then you draw two parallel lines like this to indicate the separation between this half cell, which is the anode, and this half cell, which is the cathode. And again, you have to be particular about the order in which you write these symbols. So in the case of the cathode, where reduction takes place, it's the copper 2 plus that undergoes reduction to form copper. So you write down the copper 2 plus first, aqueous, you put the molarity, you draw a line like this, and then you put a copper symbol, and that's it, right? So that's basically the cell diagram for this particular electrode. So I described that because you're going to need to do that for the question that we're going to look at right now. Okay, so with that out of the way, let me get to the assignment question. Let me see here. Let me just check the chat here. Okay. Okay, so according to this question, it says create a functional galvanic cell given the following. On the left side of the cell, there's a 1.00 m aqueous solution of oxalic acid with an inert platinum electrode. On the other cell, or the other side, there is a solid iron electrode sitting in a solution of 1.00 m iron 3 nitrate. Finish drawing the cell and label the anode, cathode, electrode solutions, and all parts of the cell. Write balance half reactions and overall cell reactions. Calculate the EMF of the cell, delta G reaction, and K, show your work. Indicate all where the charged particles flow and their identity, and also write a shorthand notation, which is the cell diagram that they're asking for. And it says use Appendix D for relevant data. All right. Now, this reminds me of something which was covered in the videos, which I'm going to talk about right now. So, based on, let me go back to the PowerPoint here. Based on rest of the topics covered in the video, they talked about the standard reduction potentials, right? I'm not going to go into it right now unless you need to ask me any questions about this, but basically what we find is that because whenever we are measuring the potential between two half cells, we need to do so by connecting one half cell to another. It's not possible to measure absolutely the potential of one half cell without connecting it to another half cell. So in order to make meaningful comparisons between half cells, what was decided was that the standard hydrogen half cell or electrode, which is abbreviated SHE here, was designed, and it was assumed that that has the EMF of 0, right? Once we assume that to have a 0 volt EMF, then basically once we hook that up to other half cells, then the other half cells measurement of EMF will be based on the fact that the standard hydrogen electrode half cell is 0, right? So people have, done a wide variety of connections between different half cells and the standard hydrogen half cell, such as connecting the zinc half cell to the hydrogen electrode. And they found that the EMF for the zinc half cell relative to the hydrogen electrode is minus 0.76 volts, all right? And then they did the same thing with copper, and they found that the EMF of the copper half cell is 0.34 volts, all right? So people continue to do that, and basically what they did or ended up with is a table such as this, and this is a very brief table. The more extensive one is provided in Canvas. Basically, this shows you the standard EMF, and you'll notice that there's an E0 here, which means that the conditions are standard. As we said before, for free energy and enthalpy and entropy, that would be temperature 25 degrees Celsius, and the pressure will be on 1 atmosphere for any gases, and the molarity of any ions or anything in solution would be 1 molar. So you'll notice if you look at this table, and it kind of looks faded, too small here. So what I'm going to do is go to the table that I have posted in Canvas, which is the one that you'll have access to. So that's this table right here, this link, standard reduction potential. Let me download that and bring that up. Okay, so this table here is what you'll have access to, right? And you notice that the topic here, at the very top, it says standard reduction potentials at 25 degrees Celsius, right? So you'll notice that all these equations here are reduction half reactions, right? In other words, electrons plus something gives you the product on the right side, all right? So these are the reactions that you'll be using and their corresponding values to answer questions like the one we're about to answer, right? So as I said before, you'll have access to this, and admittedly, this is a very comprehensive list. And one good thing about this list is that they arranged in the first half the reduction potentials. Well, they arrange it in terms of their reduction potentials, starting with the highest to the lowest. In the second half, they arrange them according to their alphabetical order of the reactants involved, starting here. All right, so you can use one or the other based on what you need to find. Okay, so let me get back to the question. Okay, so this is what we'll be looking at. And let me scroll down here. And maybe I should make this a bit smaller. Okay, and let me. Okay, so the first thing I would write down based on information provided, because the question said that on the left side, we have a 1.00 m molar solution of oxalic acid. So let me, hold on. Okay, let me get my writing thing together. Oh, shoot, hold on. I did the wrong one. Okay, and then let me do the writing thing now. Okay, so the first thing I'm going to write down here is that on the left side, we have the oxalic acid, and on the right side, we have the iron 3 nitrate solution. So here I'm going to write down on the left side 1.00 m oxalic acid, H2C2O4, and on the right side will be the 1.00 m iron 3 nitrate, FeNO33. All right. So that's the first thing I'll write down. Now, in terms of the half reactions, you'd have to go to the tables like the one that I just showed you in order to determine what the half reactions is. So I'll save us some time because I've done this already. The half reaction as far as the oxidation is concerned. Now, in order for us to do that, we needed to look up the EMF values for the half reactions involved, right? In fact, let me write the half reaction here. So the half reaction here for the oxidation will be H2C2O4 to form 2CO2 plus 2H plus 2 electrons, right? So I got this directly from the table. The reduction half reaction is Fe3 plus 3 electrons to form Fe. Okay, I see somebody said something in the chat. Oh no, that's something else. That's Skype. Okay, so you might be wondering, how do I know which is which? Well, in the case of the oxidation, when I looked up the reduction potential for this, I saw that it was equal to 0.43 volts. All right. And when I look up the reduction potential for the Fe3 plus, so this is for the reduction, right? I saw that this was equal to minus 0.04 volts, right? Now, whenever you have these two situations, the one that is more likely to occur as written is the one with the higher EMF value, right? So, in fact, I'm sorry, I misspoke. This should be minus, right? So basically, let me see here. The one that is more likely to occur as written is the one that has a higher value. The higher value would be this one right here, right? So that means that I keep this as the reduction half reaction, and then I turn this one around, right? Now, when I turn this one around, you're going to get positive 0.43. So the value here is going to be 0.43 volts, while the value here would be minus 0.04 volts, all right? And that's basically how we determine those two values, all right, for the EMF for these half reactions, right? Now, just to repeat what I just said, when I looked up the EMF value for the reduction half reaction for this equation here, this is minus 0.43 volts, and the reduction half reaction for this one is minus 0.04 volts. So because this is higher, because minus 0.04 is higher, and this is lower, right? What that means is that this equation, which you'll find in the tables, you should leave it as it is because it's more likely to occur. While the other equation that you're going to find, which is the reverse of this, you have to reverse it. Whenever you reverse it, the sign changes from minus to positive, right? So as a result, we end up with this here as the half equation for the oxidation. So that answers those parts of the question, all right? The oxidation half reaction and the reduction half reaction. Okay, before I move on, are there any questions about this? Any questions? Any questions? Okay, so if there are no questions, let me clear this. And let me get out of this and scroll down. Oh, by the way, we need to scroll up because there are some spaces here for you to answer. Now that we know which is which, we know that the oxalic acid half cell is the oxidation reaction, which is the one to the left. So therefore, we can say that this here is the anode. So let me put anode here, which means that the other electrode will be the cathode. All right. And then this will be the salt bridge, which we talked about earlier. And we talked about the role of the salt bridge in this process. All right. So make sure you complete those parts as well. All right. Let me clear this here.
Professor,
Yes, ma'am.
it's 10:51.
Oh, right. Okay, so let me take a break. So I was supposed to check the testing center to see. Okay, so let's take a break and I'll get back to you at 11 o'clock. All right. Okay, I am back. So just to give you an update, I just sent the test to the testing center. I need to call them to verify that they have gotten it. So I'm gonna do that during the next break, all right? But just to let you know that I've just sent it off. So they should receive it, but knowing how things are. Yeah, apparently when I sent the original email, I how should I put it? I attached one document twice thinking that I attached the test itself. So that's the reason why they didn't get it originally or initially, but now they should. All right.
Does
So
that mean you're gonna extend the test then?
the deadline, yeah, I guess I could do that. I'll let you guys know. More than likely it's going to be extended until maybe Monday or so. Monday, Tuesday, thereabouts.
Nicely. They
I'm
were
sorry?
they were out of appointments for me to sign up for the test because they didn't have it when I went. So
Mhm.
I was wondering if I could take it. I think another student was taking it during your office hours or something with you. Can I
Oh yes,
also join
well,
that?
not during my office hours, but a young lady said that she was going to do it with me tomorrow.
Yeah, that's
Um
me.
yeah,
Yeah, can I
so
join that tomorrow?
oh yeah, sure, for sure, no problem.
Okay, and what time?
Well, I have something to do in the morning, and that's very early. Starts at 9:30, I think. I need to verify that, but basically, I would say from to play it safe, from 11 o'clock onwards, I'll be available.
Sounds good.
All right,
Yeah, I wouldn't be able to get there until around 4:30-ish.
no problem, no problem, no problem. Just make sure you send me an email in the morning, just to remind me because I might forget stuff, you know. So, but yeah, Thursday should be no problem.
What are you doing tomorrow, Professor? I didn't catch that.
Oh no, some students said that they won't be able to make it to the testing center on campus because of scheduling issues. So I'll be available tomorrow in person for them to come and do the test with me. So that's what Thursday is all about, basically.
Okay.
Yeah. Okay. Any other questions before I move on to the rest of this assignment? Any other questions? All right. So we answered the oxidation half reaction and reduction half reaction question. So the next question is the cell reaction, which is very easy. In fact, let me rewrite what I had up here. Let me because what you have to do is add the two equations together. So what I had here is H2C2O4 to form 2CO2 plus 2H plus 2 electrons. And the EMF of that is 0.43. And then for the second half reaction is Fe3 plus 3 electrons to give Fe. So of course, in order to add these two equations together, based on what we have learned earlier, the number of electrons gained and lost must be the same, which means that you have to multiply this by 3, and you have to multiply, well, I should say multiply this entire equation by 3, and multiply this entire equation by 2, all right? Now, the key thing you need to remember here, now this is minus 0.04 volts. The key thing you need to remember here is that when you multiply any half equation by any number, these values do not change, right? These values do not change. The EMF values or the voltage values do not change, all right? That is different from what you learned concerning entropy, enthalpy, and free energy, right? In those cases, when you multiply an equation by a certain number, then you have to multiply those values by the same number. But in the case of standard EMF values, you do not multiply these values, right? You multiply the equations, but not the EMF values. In any case, the half reaction resulting or the cell reaction resulting as a result of multiplying these two and adding them together, and of course, these electrons will cancel out. The final answer, as far as the cell reaction is concerned, is 3H2C2O4 plus 2Fe3 plus And then on the product side, you're going to have 6 CO2 plus 6 H plus 2 Fe. And that would be the final equation. And then to get the EMF of the cell, you simply add this number to this number. And I got 0.39 volts as a result, right? And that's basically how we complete that table. All right? And complete, of course, the answers to the questions. Okay, any questions about this? Any questions? Any questions? All right, so let me scroll down. Let me get out of this here. And let me clear this up. Oh, I should have done this first. Okay, so let me clear that. Let me get out of that. And then let me scroll down. Oh, some more questions concerning the cell. Okay, so the shorthand notation. So if you remember what I talked about when it comes to the cell diagram, remember on one side, you're going to have the oxidation, which is the anode on the left side. And on the right side, you're going to have the reduction components, right? So just to remind you of the equations that we're working with, because you're going to use that as your guide in order to determine what the cell diagram is. So, for 1/2 equation, it's going to be H2C2O4 to form 2 CO2 plus 2 H plus 2 electrons. And then the other, so this is the oxidation or the anode reaction. And then the cathode reaction, or the cathode half reaction, is going to be the Fe3 plus undergoing reduction to form Fe. All right, so these are the 2 half reactions you're going to use to determine what the cell diagram will look like. So, as I said before, the first half would be the H2C2O4. You draw a line. You're going to have H plus. Now, they did not give the concentration in this case, so you cannot write the concentration down. Well, I guess we can assume it's 1 molar because the conditions are standard, which would mean that the concentration is H plus. So let's go with that. And then now we draw a line and we put CO2 gas, all right? Now there's one thing that I should include here because of one thing that the question mentioned, and that is that the electrode or the metal that is dipped in the solution is platinum. So you need to include that as well. So I would put that first right here, right? So what I've just written here is for the anode part of the cell. And then we draw 2 lines to show the separation between the anode and the cathode. And in the cathode part of the cell is going to be Fe3 plus line and then Fe. And again, we should assume it's 1 molar. So let me erase this here. So I'm going to put 1 molar here, and then I'm going to put a line and then Fe solid. And that would be the rest of the cell. This part here would be the cathode. All right. So that's basically how we do that. All right. Okay. Any questions about this? Any questions? Any questions? Okay. So as far as the delta G of the reaction is concerned, one formula that you should have met while watching the videos to calculate the delta G of a cell, that would be equal to minus NFE0, right? And just to explain what these terms are, N represents the number of electrons that flows from the anode to the cathode, number of electrons. And that n would be obtained when you multiply this equation by 3 and that equation by 2. 3 times 2 gives you 6. 2 times 3 gives you 6. So in this case, n will be equal to 6, all right? F is a constant known as the Faraday constant. Faraday constant. And that represents the number of electrons, it represents the charge carried by 1 mole of electrons, right? And that has a constant value of 96500 coulombs per mole, right? So for every mole of electrons, the charge carried by that mole of electrons would be 96500 coulombs. So to calculate delta G standard, based on what we just said, that would be equal to minus 6 times 96500 coulombs per mole times the EMF that we calculated earlier, which is equal to 0.39 volts, right? And according to my calculation, that works out to be equal to minus 2.3 times 10 to the 5 joules per mole. All right? So that's basically how that works out. You might be wondering where the joule unit comes from. Well, actually, it turns out that joule unit is equal to the Coulomb unit multiplied by the voltage. All right? So that is something you need to remember. And if you have done any physics, then you would have learned this. All right? So if you haven't done physics yet, then you're given a heads up here about the relationship between the joule unit, the Coulomb unit, and the voltage unit. All right? Okay. Any questions about this part, delta G calculation for this reaction? Any questions? Okay, so again, I'm going to clear this because the next part is asking for us to calculate K, which is the equilibrium constant. And we met this before. K, the relationship between K and delta G standard is delta G standard is equal to minus RT ln K. So K will be equal to E to the minus delta G standard over RT. And then we put the numbers in. So delta G from the previous part is, well, E to the minus 2.3 times 10 to the 5 joules per mole. And we divide that by R, which is 8.31 joules per mole Kelvin, times the temperature, which is under standard conditions, 298 Kelvin. So we work out all of that. And according to my calculations, this works out to be a very large number, which is 4 times 10 to the 39. And that's the answer. The joule units will cancel out. The mole units will cancel out. The Kelvin units will cancel out. So ultimately, that's the answer. Okay, any questions about that one? Any questions? Okay, so let me clear this. And let me do this, and let me scroll down. Okay, so this question is asking for you to calculate the standard EMF, the delta G standard, and K for the following reaction. So this is kind of similar to what we did earlier. However, in this case, you have to be careful because what you have to do is separate this equation into 2 half equations, all right? So 1 half equation will be, in fact, what I would do is I would go to the tables and look for the standard reduction potentials that involve these substances, right? So let me do that first. Let me make this bigger. So I did that already, of course. And when I looked it up, I saw that the reduction potential for this half reaction, 2Hg2 plus 2 electrons, to give mercury 1. The standard EMF for that is equal to 0.92 volts, right? And then when I looked up the reduction potential for the gold, getting 3 electrons to form gold itself, the EMF value for this is 1.40 volts. All right, so I had to consult the table to get these values. Now that I've done that, what I would do next is compare these two values to see which one is higher. And the one that is higher would be this one, obviously, right? So what that tells me is that this reaction will occur as written because it has a higher potential, and this one will be reversed, all right? So if you reverse this, you're gonna get mercury 2 plus to form 2 mercury plus 2 electrons. And if you reverse it, that means that the standard EMF for that half cell will be equal to minus 0.92 volts, right? So when you add these two equations together, of course, you'd have to multiply this by 2 because you have 3 electrons here, you have 2 here. You have to multiply this by 3, all right? So when you do that and add them up, you're going to get 2Au 3 plus 3 mercury 2 plus, and then on the right side, you're going to have 2 Au solid plus 6 mercury 2 plus. All right, so that's what you get when you add these two equations together, and then you add the two EMF values together to get the answer. When I did that calculation, I got 0.48 volts. 0.48 volts, right? Now, another way of doing this, which you might find simpler, is that you should use this formula. The EMF of the cell is equal to the EMF of the cathode minus the standard EMF of the anode. All right? And these are all standard values. So I'm going to symbolize it as such. Now, you can identify which is the cathode because, again, this is the higher value here. So therefore, this would be the cathode half reaction. And this would be the relevant EMF for the anode, even though the half reaction will be the reverse. So basically, all you'd have to do is plug in the values, 1.40 volts minus 0.92 volts, and you're going to get the same answer as we did before, which is 0.48 volts. All right. Now, we're not finished yet because you'll notice that this equation here that we just determined is the reverse of this equation here, right? And the question is asking for the EMF of that equation. So basically, that's very simple. That means that the EMF of this equation here would be minus 0.48 volts. Because this equation here is the reverse of the equation for which they're asking for the EMF. So this would actually be the final answer as far as the standard EMF of this equation is. All right? Okay, so any questions about that? Any questions? Okay, so the rest of this you should be able to do. So let's see what you can come up with. Is it okay for me to clear this? Going once, going twice. Okay, so the next question is asking for us to calculate delta G standard. So how would you calculate that? Anybody?
You would find the negative NFE standard.
Okay, NFE standard, very good. So in this particular case, what is N?
-6.
Okay, so 6 times Faraday's constant, which is what?
96500.
Coulombs
However
per-
you say coulombs
Yeah,
per
coulombs.
mole.
Yeah, this is how I spell it. COULOMBS, coulombs. And then we multiply by the EMF that we calculated, which is minus 0.48 volts. And that's it. Work that out, and let's see, what did I get? I got, oh, this is wrong here. This should be 9650. Okay, so when I worked this out, I got, okay, I did not round it off correctly. So the correct answer is 2.8 times 10 to the 5 joules per mole. So that's the answer I got for delta G standard. Okay, very good. And then the next question was K. So let me get rid of this here. So K. What is K equal to? The equilibrium constant. What is that equal to?
E to the negative delta G over RT power.
Okay, very good. So we just calculated delta G. That's minus 2.78 times 10 to the 5 joules per mole, and divided by R, which is 8.31 joules per mole Kelvin. And we multiply that by the temperature, which is 25, or I should say 298 Kelvin. All right, so let me see what I got when I did that. I got 1.82. In fact, let me just show you the steps, because what I have here, I jumped a couple of steps. So what I got when I did this part here, when I did all this here, I got this equals to E to the minus 112, right? And then when I did that on my calculator, this turned out to be equal to 1.82 times 10 to the minus 49. And that's basically how that is done. All right. Okay, any questions about this? Any questions? All right. So what I'm going to do now is go to the addendum, excuse me, addendum part for assignment number 7. So as I said before, there's another link for that. Let me get out of this here. In fact, let me clear this, get out of that, and then go to, okay. Now, this addendum here deals with a different type of electrochemical process, because the previous assignments that we did, we were assuming that the reactions are producing energy, right? Spontaneous reactions taking place in the cell, and the result would be energy would be produced in the form of electrical energy. Now, in this case, we're talking about an electrolytic cell. And in fact, just to give you a brief description of what's happening, in those cases, I am going to go to the PowerPoint here. This was already covered in the videos, but I just feel as if I think I need to talk about electrolytic cells. In the case of electrolytic cells, basically what is happening is that we're using a chemical reaction. We're using an electric current to drive a chemical reaction which would be otherwise non-spontaneous, all right? So in other words, let me see here. So in other words, we're using an electric current to drive the non-spontaneous reaction that will be taking place. We call this electrolysis, right? And these are 2 examples right here. I'm going to use this. The same principle applies here, but I'm going to use this diagram here to show you exactly what's happening. So in this particular case, we have a solution of sodium chloride. Actually, not solution, it's molten sodium chloride. Molten meaning that basically we're talking about sodium chloride in a liquid state. And as you can imagine, sodium chloride being an ionic compound, in order for you to get it to the liquid state, you have to heat it to a very, very, very high temperature, all right? So you stick two electrodes in, you connect it to a battery, and you allow the current to flow through. And what will happen is that at the anode, oxidation takes place, just as in the case of a galvanic cell, right? What will be oxidized in this part of the electrolytic cell is the chloride, at least the chloride. So the chloride is going to undergo oxidation. What's going on? Oh, I'm sorry. The chloride will undergo oxidation to form chlorine. So you're going to have chlorine gas being formed at the anode. At the cathode, what will happen is that the sodium ions, which will be floating around, will be reduced to form sodium. So you're going to have sodium forming at the sodium, at this cathode right here. So basically, that's what happens. Otherwise, this reaction will not take place. Sodium chloride will not spontaneously react to form chlorine and sodium. So the energy for that reaction comes from the electricity source here, which would be the battery right here, all right? Here's another example, the electrolysis of water, right? Now, in this case here, what will happen is that at the anode, oxidation will take place. And what will be oxidized will be the water, right? Water will undergo oxidation. You get this reaction right here. In the case of the cathode, it's the hydrogen ions present in the water that will undergo undergo reduction. And that's what happens here. As a result, you're going to have hydrogen forming at the cathode and oxygen forming at the anode. And you'll notice that there's a 2-to-1 ratio between the hydrogen being formed and the oxygen being formed. And if you were to actually do the experiment, this is what it's going to look like. And as you can see clearly, the hydrogen which is trapped here compared to the oxygen that is trapped here, there's a 2-to-1 ratio in terms of the volume, which corresponds to the 2-to-1 mole ratio between the hydrogen and the oxygen that is produced at each of the electrodes, all right? Okay, so I just thought I should mention that. Maybe I should talk about this as well. We can actually do some quantitative calculations based on what we just discussed with respect to electrolysis. Key thing you need to remember here is this equation right here, which again, if you're going to do physics, you're going to meet this equation. The charge carried by a current will be equal to the actual magnitude of the current, which is measured in amperes, multiplied by the time in seconds, all right? So basically, if you know the charge that is passing through a particular solution, and if you know what is being oxidized and what is being reduced, you can actually do some calculations based on what is shown here in the flow chart to determine how much of a particular substance will react or how much of a particular substance will be produced as a result of the electrolysis, right? So this flow chart here basically summarizes the steps that you'll go through. It talks about, firstly, if you know what the current and time is, you can determine the charge, and then you can divide by the Faraday constant, the charge that is, and that will give you the number of moles of electrons. Then, based on the half equation, you can determine the mole ratio between the electrons and whatever you're trying to calculate. The moles of substance that is oxidized or reduced can be calculated based on that. And then, depending on what the question is asking for, you can determine the amount of the product or the amount of substance being used up based on either the molar mass or the ideal gas equation if you're dealing with gases, right? Again, this is what you're going to use at this stage right here. 1 mole of electrons will carry a charge of 96,500 coulombs, all right? Okay, so let me go back now to the assignment. So let's see if we can answer these questions together, all right? It says, in an electrolytic cell, the negative electrode is negative because it has, is it too many or too few electrons? Too many would be correct. So let me put the answer here. So, or in fact, let me just circle the answer here. Okay. Okay, so the next question is the chemicals that come into contact with the electrode will what? Well, if the electrode that is negative will have too many electrons, then what will happen to the chemicals that come into it? Will it gain or lose electrons?
Will they gain electrons?
Exactly, they will gain electrons. And be what? Is it
Reduced.
oxidized? Reduced, exactly. The electrode in electrolysis, the negative electrode in electrolysis is called what?
The cathode?
Exactly. Okay, very good. So that answers number 1. Number 2 says, write the change that water goes through at the electrode. Now that was given earlier in the discussion I just had. Let me just do it for you. Water plus electrons will give hydrogen plus OH minus. And to balance this, we're going to need, okay, what we're going to need? We're going to need a 2 here and a 2 here. And that is it. All right. So this will be the equation which describes the reduction of water at the cathode. All right. Okay. Let me clear this and scroll down. And basically they're asking similar questions in this section for the other electrodes. So let's go through this. So in an electrochemical cell, the plus electrode is positive because it has what's the answer? Too few or too many electrons?
Few.
Too few. Very good. Very good. Chemicals that come into contact with the positive electrode will what?
Lose.
Lose electrons. And B?
Oxidized.
Be oxidized. The positive electrode in electrolysis is called what?
Anode.
Exactly. Okay, now for this one, I'm going to help you out here a bit. For this one, when the water undergoes oxidation, it's going to form H plus O2. And to balance this, plus electrons. And to balance this, we're going to need 4 of these here. That's okay. And here we're going to need 4 electrons. So this is the reaction that water would undergo at the anode. All right. Okay, any questions about this? Any questions?
I had a question about the last equation.
Uh-huh.
Because you had 2 hydroxides, wouldn't it be 2 electrons? Not for this one, but the last one that you
Oh,
wrote?
the last one? Okay, what did I write down for the last one? Let me
You wrote 2 H2O plus electrons, but since there's 2 hydroxides.
H2O plus 2 electrons to give was it hydrogen?
Yeah, H2
And
plus
plus
2
2.
OH minus.
Uh
So it would be 2 electrons.
yeah, it
right?
will be
'Cause
2
you had-
electrons. Oh, so
Okay.
did I just have
I-
one?
I think so. At least that's what I had written.
Okay, well, that would be a mistake on my part. This is 2
Okay,
because
perfect. Thank
because
you.
the charges would have to be balanced. All right. Okay, any other questions before I clear this? Any other questions? All right, so let me clear this. Let me scroll down. Oh, I should have erased them because the next question says you need to add these 2 equations together. Make sure that the electrons cancel. Okay, so let me rewrite the 2 equations So let me, okay, so one equation was H2O plus 2 electrons to form H2 plus OH minus. And the other equation was H2O to form H plus what did I say? H plus plus electrons plus O2, right? Okay, so and to balance this one, I'm going to need a 2 here, 4 here, and this one is, oh, I'm going to need a 2 here. Okay, so basically what they're saying, oh, and I'm going to need a 4 here. So basically what they're saying is that you need to add these 2 equations together. Of course, we need to make sure that the electrons are equal. So that means that we need to multiply this one by 2. So let me erase this here. Let me multiply this equation here by 2. So you're going to end up with 2H2O plus 4 electrons to form 2H2 plus 2OH, 4H minus. And then we add these 2 equations together. These 4 electrons will cancel with those 4 electrons. You're going to end up, yes, ma'am.
When you wrote down the first equation for when it goes through at a negative electrode, you had 2 H2O.
Right. So that means this should be 4. Yeah, okay. Let me see. Anything else will cancel out? No. So basically we're going to have, hold on, something is wrong here. 2H2, that's 4 hydrogens, 4 hydrogens, 2 oxygens. Okay, so that's balanced. So that's balanced. Okay, so let's continue. So this will be 6 H2O to give 4H plus 2H2 plus 4OH minus. Okay, now here's the thing about this. These 2 will combine to give you 4H2O, right? And if you subtract these 4 H2Os from both sides, you're going to get 2 H2Os. So, and I forgot the O2 here. So the final answer will be 2 H2O to form 2H2 plus O2. So this would be the final answer here. All right. Okay, any questions about this? Any questions? All right, let me clear. Can I clear this? Going once, going twice. Okay, so let me clear this. Let me stop this. And let me continue. Okay, so this question says, we will perform this electrolysis using an aqueous solution of sodium sulfate. Both sodium and H2O will be near the electrodes. Which chemical is more likely to be reduced? All right, now this is a very interesting question, because what will happen is that you have a solution of sodium sulfate. The sodium ion will be attracted to the cathode, right? Because the cathode is negatively charged, the sodium ion is positively charged, right? So there's a potential of this reaction taking place. I'm not saying that it will take place, but there's a potential of this reaction taking place. Na plus electrons to give Na, right? But there's also the possibility of water undergoing reduction like we described before, which would be hydrogen plus 2OH minus plus, no, that's it. And to balance this, we're going to need 2 here, and this will be 2 electrons here, all right? So these are 2 possible reactions that could take place at the cathode. Now, the question is, which one will occur? And the answer lies in looking up the EMF value for each of them. Now, unfortunately, I did not get a chance to do this before class, so I'm actually going to look up the EMF values for both half reactions. So let me go to my table here, and you can look at it as well. It's in Canvas, as I said before, and confirm that I'm writing down the right things. So in the case of the sodium, if I can find it. Okay, so I found it. In the case of sodium, the value that I observe here is minus 2.71 volts, right? In the case of water undergoing reduction, let me see here, where will I find? Okay, water. In the case of water undergoing reduction, where is it? Where is it? Where is it? I just. Okay, where are you? Where is it? Water. Okay, where are you? Okay, should be here somewhere. I know I saw. Oh, here it is. Okay, so in the case of water undergoing reduction, the EMF value for that is equal to minus 0.83 volts. Okay, I'm losing power on my laptop here. Okay, what did I say? Minus 0.83 volts, right? So, of course, as I said before, the one with the higher potential is the one that's most likely to occur. So obviously, this is higher than this. So therefore, we know we can predict that this is the reaction that will take place at the cathode. All right? So the answer would be that it's H2O that will undergo reduction at the cathode. All right? So basically, you have to consult the table in order to answer a question like this. All right? Okay, any questions about this? Any questions? Any questions? All right, now, basically, we have to do something similar for the other part, number 7. Let me scroll down to number 7. The only difference is that it is oxidation that we're looking at, right? We have to predict, well, firstly, sulfate would be one of the substances that will undergo or that will be attracted to the anode, and the other would be, again, water. So the question is, which of those would undergo the reaction of oxidation at the anode? So again, we have to consult the table, but now you have to be careful. And let me explain what I mean by that. If you consult the table and you look up the reduction reaction, or I should say the reaction where water is oxidized, you will not see that equation because the table contains only reduction half reaction. So you have to look for the table, or you have to look in the table for the values for the reverse reaction. So the reverse reaction, now remember, the oxidation reaction is H2O to form 2H plus O2 plus 2 electrons. So what you have to look for is this, 2H plus O2 plus 2 electrons to form H2O, right? That's what you have to look for, need a 2 here. So you have to look up the equation and the corresponding EMF for that, all right? So let me see if I can find that right now. Again, unfortunately, I did not have the chance to do these problems, so I'm doing it along with you guys. And let me see. So I'm looking for H plus. Okay, H plus. Plus O2. Okay, so this should be 4 here because you have 4 hydrogens here. And when I looked it up, this is what I found. I found that the EMF of this is 1.23 volts, right? And then I would look for any reaction where the sulfate is the product of the oxidation. I don't know what that is, so I'll have to look that up in the table. So let me see if I can find that now. See if I can find that. Okay, so the only equation I see here where the sulfate is the product of a reduction is this one here, S2O8 with a -2 charge plus 2 electrons to give you 2 sulfate ions. And according to this, the EMF of this is equal to plus 2.05. Right? Okay, so these are the 2 reduction reactions, but remember, we're looking at the oxidation. So for the oxidation or the reverse of this, the EMF here will change to minus 1.23 volts. And for this one, when you reverse it, the EMF of this would be minus 2.05 volts. Right? Now, because this is higher than this, we can
Professor?
therefore, I'm sorry?
I'm a little confused. I thought you
Okay.
already reversed the first equation. Well, reverse them.
Yes, I did reverse them. But the reason why I reversed them is because I need to look in the table to see these equations here, right? So that I can identify their EMF values.
So you're
But
going to reverse
remember-
them and then reverse them again.
Yes, and the reason why I do that is because we're looking for what will happen when oxidation takes place. You see, these are reduction reactions. You see what I'm saying? These 2 equations, this one that I wrote here and this one here, these are both reduction half reactions because in both cases, you're adding electrons to the left side. Right? But what the question is asking for is which chemical will be oxidized? In other words, will it be the water or will it be the sulfate? So we're talking about the reverse. Which one was more likely to be reversed? And the answer would be this one, because when you reverse it, its potential would be higher compared to this one. So the answer here would be H2O. I know it's kind of confusing, but you have to kind of keep things clear about what the question is asking for and what you have at hand in your table. Right? The table gives you only reduction potentials. So if you need information about oxidation, you'd have to reverse those potentials. You have to reverse the equations and change the sign of the potential from what it was before to the opposite sign. All right? Okay, any questions about this one? Any other questions about this one? Okay, I'm going to take a break now. And in the meantime, what I'll do is call the testing center. I'll let them know that I've send the test over. So I'll be back at 12 o'clock. Okay, folks, I'm back. All right, so let me whoops. Let me clear this here and scroll down. And basically we're going to continue with this question, which is essentially similar to what we discussed earlier. So it says here, in the electrolysis of potassium iodide, both the potassium and water will be near the electrodes. So the question again is, which will be more likely to be reduced? So again, I would have to go look for the table and see what the value for the reduction of potassium is. If I can find it, 1 minute here. Okay, so as I said before, let me just rewrite or write down the equations. For K plus, the reduction equation would simply be this. And for water, as we said before, is going to be H2 plus 2H minus. We need a 2 here and a 2 here, all right? So basically, again, we need to find out what the EMF value for the reduction of these two, the reduction half equations for these two half cells. So the one for water, we had it before. Can somebody remind me what that value is?
Negative 0.83 volts.
0.83 volts. Yeah, that saves me from searching for it again. Now for the potassium, let me see if I can find it here. Okay. According to the table, the value for the potassium is minus 2.93 volts, all right? So obviously this is higher. So that means that water is more likely to be reduced at the cathode in this particular situation, all right? So that's relatively simple. So that's as far as that is concerned. So let me clear this here. And let me scroll down. Now this one is a bit more challenging. Let's see here. Iodide and water. Now, in the case of the iodide, I should have created more space in this handout here, but let me do this up here. So in the case of iodide, the oxidation would be iodide to form iodine plus 2 electrons. I need a 2 here. And in the case of water, the oxidation would be O2 plus 2H plus 2 electrons. In fact, 2 here, 4 here, and 4 here. And again, can somebody remind me of the oh, okay, well, before we do that. So basically, we have to find out what the EMF of this and this is, right? Now, the EMF of this, okay, can somebody tell me what this is? We did this before. Remember, it was
You
the
need
reverse of
positive.
it was the reverse of the oxidation.
Do you need the positive or negative value?
Hold on, which one did I give first?
The positive, but it was the reverse of what you have written on the screen.
Right, so I need a reverse of, okay, so that would be negative then.
Negative 1.23 volts.
1.23 volts, all right? Okay, so what I'm going to do now is look for this equation, right? And when I look for it, this is what I found. I found that the EMF of that is equal to 0.5 plus 0.54. Okay, so that means that for this, when I turn it around, the EMF here would be equal to minus 0.54 volts, right? So between these two, which one is higher?
The iodine.
Right, the minus 0.54 volts, right? Which means that it is the iodide that will undergo oxidation at the anode, right? So basically, the cathode reaction is going to be what we had before. I keep forgetting. It's H2O plus 2 electrons to give OH minus plus H2. We're going to need 2 here, 2 here, and 2 here. And the anode reaction is going to be 2I minus to form I2 plus 2 electrons, right? So the overall equation is 2H2O plus 2I minus to give 2OH minus plus H2 plus I2. So that would be the overall equation that would take place in that particular cell.
Professor,
Alright.
somebody put something in the chat.
Oh, let me see. And they say they have the same issue with having only tables and oh, I guess this person. Let me quickly reply to this person. Okay. All right, thank you. Okay, any questions about what we just did? Any questions? Any questions? Any questions?
Wait, Dr. Nicely,
Mhm.
you sent the test to that email I just put in the chat?
Oh, I'm sorry. It was you?
Sorry, yeah.
Oh,
This
I-
is
I-
different than the one you had that you
oh,
were talking
my
about
bad,
earlier.
my bad. Okay, I'm going to send.
Yeah, no
okay,
problem.
I'm going to send it during the break, during the next break. I thought it
Would you
was.
be
I
able
thought
to
it was.
send it? Wait, that's at 12:50?
I could do that.
Would you be able to do it any sooner than that?
Okay.
Because I
let
have
me
to
do-
go to work after I'm done taking this exam.
Okay, let me tell you what. What I'm going to do is forward the email I just sent to the testing center. Let me see if I can. Where is it? Where is it? Where is it? Where is it? You know what? Let me do this. Come on. Okay, so let me forward. And the email address that you sent me is taylor.lewis at us.af.mil. Okay, just sent it over.
All right, thank you so much.
Yeah, no problem. All right. Okay, so going back to this now. What was I saying? So any questions about this we just did? Any questions? If not, then I'm going to clear this and scroll down. Okay, similar exercise here. Now, in this case, it's copper 2 sulfate being electrolyzed, right? So one equation would involve, okay, let's deal with what will be reduced first. So basically what will end up at the electrodes to potentially undergo reduction will be Cu2 plus 2 electrons to form Cu, and H2O plus 2 electrons to form 2OH minus plus H2, right? Okay, again, remind me of what this was. The EMF for the reduction of water is what? Hello, what's the reduction potential for the reduction of water?
Sorry, I was looking back at my notes. It looks like
Oh,
it's negative 0.83 volts.
0.83 volts, okay. And then let me look up the value for the copper 2 plus reduction. Okay, so according to the table here, the EMF for the reduction of copper 2 plus is equal to 0.34 volts. Okay, so which one is higher? Obviously this one, right? So therefore, copper 2 plus is more likely to undergo reduction compared to water. So the answer here would be copper 2 plus, all right? Now for the sulfate and water, let me erase what's up here. In fact, you know what? Let me go to this here. I find this more convenient to use. Okay, so in the case of copper, I'm sorry, the sulfate and water, what we're looking for is the reaction where sulfate is undergoing reduction. We did that before. If I remember
it looks like
correctly.
it was number 7.
Hold on. It was 2 electrons. What was the EMF for this?
2.05.
2.05.
And
And
then when you
then-
reversed it, it was negative 2.05.
Okay, very good. Now for the other, hold on. For the water that is being reduced. No, what am I doing? That is being oxidized. It's H2O, would be over here. And what the reverse reaction is 2H plus 2 electrons plus O2. In fact, it should be 4H plus 4 electrons. And this would be 2H2O. What was the EMF of this?
1.23.
1.23, right? So basically, if you reverse this, you're going to get 2 SO4, 2 minus to form S2O8, 2 minus plus 2 electrons. And the EMF of that would be minus 2.05 volts. And if you reverse the other one, which is the oxidation of water, that would be 4H plus. Plus 4 electrons plus O2, and the EMF of that would be, of course, minus 1.23 volts, right? So between comparing these two, this one is higher, which means that water is more likely to undergo oxidation at the anode. So that means, going back to the assignment here, it is going to be the copper that will undergo reduction. As we said before, the copper 2 plus, that is, will undergo reduction, and it is the water that will undergo oxidation, all right? So the cathode reaction is going to be Cu2 plus 2 electrons to form Cu, and the anode reaction is going to be H2O plus, not plus, but oxidize to form H2, 4H plus 4 electrons plus O2, all right? So to add these two together, we would have to multiply this equation by 2 so that you're going to have 4 electrons here, which cancels out the 4 electrons on the right side. So the final answer is going to be Cu2 plus H2O to form 4H plus Cu plus O2. And that would be the final answer. Let me see here.
Didn't
Just a
you
minute.
add a 2 in front of the Cu2
Yes.
plus and the Cu?
Yeah,
Yeah.
exactly. Mhm. Okay, so that's basically how that is done. All right. Okay, any questions about this one? Any questions? Any questions? Okay, so let me clear this and scroll down. Okay, all right, number 10 says silver plating occurs when the electrolysis of silver sulfate solution is used because silver metal is formed at the, okay, so what do you think the answer is? Will silver be formed at the cathode or the anode? Remember, the cathode is negatively charged and the anode is positively charged. And let me remind you that silver sulfate will dissociate this way. All right, so which of these two would be attracted to the cathode or would be formed? I'm sorry, let me scratch it out. We're talking about electrolysis. Silver will be formed in the solution, but the electrolysis is basically will result in silver being formed at one of the electrodes. So the question is, which electrode will this reaction take place? Is it the cathode or the anode?
It'll be the anode.
Nope. Folks, you need to remember this. Oxidation takes place at the anode, reduction takes place at the cathode, always, right? That is true for galvanic cells and true for electrolytic cells, right? So the answer actually is the cathode, because silver ions would have to be reduced, and therefore that's where it gets the electrons, from the cathode. And the next question is, is it positive or negative electrode?
Negative.
Negative, all right? And then the question says the reaction at this electrode is, well, what you can do is just write this down here, all right, to answer that question. All right? And that's basically it for number 10. All right, let me clear this. Scroll down to number 11. Now, number 11 says, recall that 1 ampere second is equal to 1 coulomb, and 96,500 coulombs equal to 1 mole of electrons, and that's Faraday's constant. So the question here is asking, if a cell is run for 200 seconds with a current of 0.250 amperes, how many grams of silver will be deposited? All right. So basically, we're going back to the equation I just showed you. Which shows you that silver will gain electrons to form silver. And if you look at this equation, there's a 1-to-1 mole ratio between the electrons and the silver, right? So basically, if we can find out the number of electrons here, we can find out the moles of silver and eventually the mass. So how can we do that? Well, the first thing we need to do is find out what the charge is. Q is equal to the current multiplied by the time. I is usually used in physics for current, T is for time in seconds. So the current is 0.2 0.250 amperes multiplied by the time. Now the time has to be in seconds. And they gave us the time in seconds, so that's good, right? So that would give us the amount of coulombs, which is what? Where's my calculator? So that is 0.25 times 200. So according to my calculation, that would be equal to 50.0 coulombs, all right? So that's the amount of charge. So let me just rewrite that down here, 50.0 coulombs. What we need to find is the moles of electrons, and that's where Faraday's equation or Faraday's constant comes in, right? For every 1 mole of electrons, the amount of charge carried is 96,500. So I'm going to put 1 mole of electrons up here and 96,500 coulombs down here. And that will give us the moles of electrons. Now, based on this equation, there's a 1-to-1 mole ratio between the silver and the electrons. So we can represent that in the next conversion factor where we have 1 mole of silver and 1 mole of electrons. So this will cancel out with that, but we're not finished yet because the question is asking for the mass in grams. So in other words, we're going to need what? What are we going to need to calculate the mass in grams from the moles?
Molecular weight of gold, silver, whichever, Ag.
Yeah, well, more specifically the molar mass, to be more accurate, but you have the right idea. So let me look that up now. And according to what I have here, the molar mass of silver is 107.87 grams of silver. So this is basically the setup. And now we have to do the number crunching. So that's 50 divided by 96500 times 107.87. And according to my calculations, this works out to be equal to 0.0559 grams of silver. And that's basically how that is done. All right. Any questions about this particular problem? Any questions?
Yeah, what is I again?
The current. I'm sorry. This should be the current, C-U-R-R-E-N-T, which is measured in amperes. And T is the time, which is measured in seconds. And this is the charge, which is measured in coulombs. So this is a charge. All right. Okay, any other questions about this problem? Any other questions? Any other questions? Okay, moving along. So I take it it's okay for me to clear this, right? Going once, going twice. Okay. And let's scroll down to number 12. Okay, now number 12 is interesting. Number 12 says you have a current of 10 amperes flowing for 2 hours through an electrolytic cell containing a molten salt of metal X. All right, so we don't know what X is. This results in a decomposition of 0.250 moles of X at the cathode, right? So the question is asking, what is the oxidation state of X in the molten salt, right? So I guess these are the possibilities, +1, +2, +3, +4. All right, so how shall we tackle this? Let's see here. Well, the first thing I would do is I would try to find Q, the charge, which is, as I said before, the current multiplied by the time. So the current is 10.0 amperes. And you'll notice that they gave us the time in hours. So we have to do some conversion here. It's 2.00 hours. We'd have to convert that to seconds. So for every 1 hour, there is 3,600 seconds. All right. So we work that out to get the charge total. That's 10 times 2 times 3,600. And according to my calculation, that works out to be equal to 72,000 coulombs. All right. The hours will cancel out. The amperes times seconds gives you the coulombs. All right. Okay. And also what I would do, let me continue that down here. I will determine the number of moles of electrons. So 1 mole of electrons will carry a charge of 96,500 coulombs. And let's see what that gives. So 72,000 divided by 96,500 coulombs. And the answer I got here is 0.7. Okay, when rounded out to 2 sig figs, that will be 0.75 moles of electrons. All right. Okay. So we don't know what the charge is. I'm just going to write a hypothetical equation here. So this is the metal here. This is the charge on the metal. In order for the metal to be deposited, you need to add n electrons for every mole of this to get a mole of the metal, right? Now, the question says that the moles of the metal is 0.75, no, what am I saying? 0.25 moles, 0.25 moles, all right? So basically, the mole ratio between the electrons, let me do this here, mole ratio of the number of moles of the metal, X, divided by the number of moles of electrons would be equal to, let me see here. The number of moles of the metal is 0.25, 0 moles, and the number of moles of the electrons would be 0.75. So just by looking at this, you can tell that this is a 1-to-3 mole ratio, all right? So what does that tell us? That tells us that the number of moles of the electrons will be equal to 3 times the number of moles of the metal, right? So what that tells us, therefore, is that N is equal to 3 here, which means that the charge on the metal ion is going to be +3. All right. Okay, any questions about this particular problem? Any questions? Okay, so that's basically it as far as this assignment is concerned. So again, I'm expecting you guys to complete it. Make sure it looks neat and tidy and submit it online. And what I'm going to do right now is create a Dropbox for it. This is
Do you want
assignment.
us to submit two separate, is there going to be 2 separate drop boxes?
Actually,
Or do you
no.
want to put us together?
Yeah, together.
Okay.
Together. Good question. Yeah. Please submit it together because it actually should be one assignment. So this is assignment number 7. And let me see here. Okay, so you should be able to, hold on, let me see here. Let me see. Okay, so today is the 26th. So I will let the due date for this be the 28th, which is Friday.
And do you know if we're going to have class on the 9th of August?
I'll have to look at the schedule. Why do you ask?
Well, because I know that that's the last day of classes per se, but that would be the week that we're doing the final. So, and that would have to be due by Wednesday. So I'm just wondering if we're going to have all the information for the final before then and we won't have class, or.
All right, hold on 1 minute. Hold on 1 minute. Okay, so classes end on the 9th. And today is the 26th. Let me just look at the calendar here. Okay, so basically we have one more week. So basically we have 2 days of classes. One will be the 31st, the other one will be the 2nd. So yes, because actually there's only one more chapter left after electrochemistry, and that's nuclear chemistry. So I anticipate that we should be finished with nuclear chemistry definitely by Monday. Because nuclear chemistry is not a long chapter itself. So yes, you should be able to get all information in that you're going to need for the final. As far as test number 3 is concerned, that is going to be due on the, let me see here. It's going to be the week of the 31st, right? And I'll let you know what that test will be on. But I would say, just based on what we have covered so far, that test will be covering the chapter dealing with solubility product and all that, titration, buffers, and so on. And the chapter after that, which is thermodynamics. Yeah, so I think those are the 2 chapters that will be covered in test number 3. And then the final will be comprehensive, covering all the topics. So yes, I anticipate that we should be able to complete everything by then.
So that would mean we wouldn't have class on the 9th?
No, because the final exam is due, let me see here. According to the academic calendar, the grades are due on the 10th, classes end on the 9th. So basically the only thing you should be doing that week would be the final exam, and that would have to be definitely done by the 9th, because I have to grade them. In fact, I would say by the 8th, because I need to collect them and grade them and submit the grades by the 9th.
So
Or
we
by
would
the
only
10th.
have 2 days to take the final,
Yeah.
the Monday and Tuesday?
The Monday and the Tuesday. Because if I wait until, unless, okay, let's put it this way. If I were to give you guys on the 9th, I'd have to collect it like midday or something like that, because I have to be grading them and submit them by 10 o'clock the next day.
So would we not have class on Monday? That way we would have time to go take the test, because I work Monday nights and I have my last lab on Tuesday. That would take my time.
Let me see here. So the Monday would be the 7th.
Correct.
So let me see here. Today's the 26th. We definitely will be finished with nuclear chemistry by next Monday. I guess we can not have class on the 7th. What I can do is make myself available for any questions during the regular class time. But to answer your question, yes, I mean, I don't see any reason to have class. If we're going to finish with the syllabus by Monday, right? And then there's Monday, there's Wednesday. I mean, we could use that class for review purposes. And then, you know,
I
the
think
7th.
that's a great idea.
What's that?
I think that's a great idea to use
Yeah,
the
I mean,
Wednesday for
yeah.
review.
Right, exactly. I have no problem with that. I have absolutely no problem with that. So, okay, with that in mind, what I'm going to do, I'll probably, if I get a chance, just post an announcement later on today that we'll be reviewing on the last day for lecture itself would be the 31st, and then we'll be reviewing for the final on the 2nd, which is the Wednesday. And you guys have to ensure. In fact, what I'll probably do, come to think of it, let me see here. What I'll probably do is make the final available from Thursday, which is the day after, until the 8th, to give you guys more time. If you guys want to, if you guys, you know, if some of you guys want to do it on the Thursday, the 3rd, because the campus will not be open on Friday. Otherwise, I'll make it available on Friday. And then 7 and 8, and that's it. Well, 7, 8, and 9, I should say. But the 9th, I would suggest you guys, if you're going to do it on the 9th, do it as early as possible, because I'm going to pick up the papers like at midday, because I'm going to need time to grade them. All right. Okay, any other questions? Okay, so what I'm going to do for the rest of the time to speed up things a bit is to go directly into the nuclear chemistry chapter. So let me go, hold on 1 minute. Let me go here. Oh, let me clear this first.
And you said the nuclear chemistry is the last chapter we'll be working on, right?
Yes, yes, ma'am. And it's a pretty short chapter. I mean, you'll see. Okay, so let me go to lecture notes.
This assignment number 7, will this
Mhm.
material be on our exam that's coming up next week, or will that be on the
I
final?
I don't think so. I'm just going to make, that would be a part of the final, but not the next exam. The next exam will cover things like buffers, titration curves, solubility product, and then the chapter following that is thermodynamics. So I think I'll just make it be about those two.
Okay,
And
thank you.
then the rest will be on the final. Okay, so let me where is it? Nuclear chemistry. Let me publish that now. And let me see here. I just want to check something here. Okay, so let me publish that right now and download. Okay, nuclear chemistry. So first thing I'm going to mention here is a review, right? Basic review, because this will become important later on. So I'm quite sure by now we're all familiar with these terms. Atomic number, mass number. The atomic number is basically the number of protons in the nucleus of an atom. The mass number is the sum of the number of protons and neutrons. So basically, if you know the atomic number and you know the mass number, you can determine the number of neutrons. Now, another thing you should remember is that each element has its own unique atomic number, right? So carbon is the only element that has atomic number 6. Sodium is the only element that has atomic number 11, and so on and so forth. So it is the atomic number that basically we use to identify the unique particular atom of the element. Now, this here is the universal symbol that we use to combine all these different types of information for a particular atom, right? A is the mass number, right? And that is typically written on the left side as the subscript. Z is the atomic number, which is written bottom left of the symbol of the element as a superscript, and the X would represent the symbol of the element, right? So, you know, this is basically what is accepted all over in chemistry and physics in terms of what we call the isotopic symbol. We call it the isotopic symbol, which gives you all that information. Now, in nuclear chemistry, we'll be concerned with the nature of different particles. The first of which is the proton, right? So the proton is, of course, an integral part of any atom. And we symbolize the protons by using either this symbol or this symbol, right? Any one will work, all right? So the one here, the bottom one, would be considered to be the atomic number. The top one would be the mass number associated with the proton. Then we have the neutron, which is also a very important part of the nucleus of most atoms. And here we see that the symbolism that we use for the neutron is a 1 up here and a 0 here, and N, of course, which would represent neutron, right? So the mass number in the case of the neutron is 1, and it is considered to have no charge because it's neutral, all right? Then a third particle that we'll be concerned with. Now, this one is a bit unique because in this case, the mass is considered to be 0. Now, the actual mass is not 0. It's actually less, much less than the mass of a neutron or proton. But for all purposes, we say that the mass number is 0, right? Because we said that the mass number is the sum of the number of protons or neutrons. There are no protons or neutrons in the electron. So therefore, we just say that the mass number is 0. And another unique thing about the electron, or, well, we also call this a beta particle. I'll get to that shortly. But the other unique thing about the electron in terms of how we represent it in a shorthand fashion is that we say that the atomic number is -1, right? Which is a bit of a contradiction, because if we were to go by the strict definition here of the atomic number, it says the number of protons in the nucleus. That's the definition, but we just use -1. And this is for the sole purpose of the convenience of balancing nuclear equation, which we're going to see shortly. So this is one way of representing the electron. Now, another way of representing it is using this symbol here. You might recognize this here as a Greek letter beta. So the alternative name for the electrons when it comes to nuclear reactions, we call it a beta particle, all right? So the mass number is said to be 0, and the atomic number is said to be -1 in the case of a beta particle. Then we have a fourth particle, which is considered to be the opposite of the electron or the beta particle, and we call it the positron, right? And the only difference between the positron and the electron is that the atomic number is said to be +1, all right? So that's another particle that you'll be encountering in this particular chapter. And then the last particle here that we're going to talk about here is what is called the alpha particle. The alpha particle is the same thing as the helium-4 nucleus, right? Where the atomic number is 2 and the mass number is 4, all right? So that is one way of representing it. And here we have another symbol here to represent the alpha particle. All right. Okay, so those are some of the particles that you'll be meeting from time to time, because these particles are oftentimes involved in a lot of nuclear reactions that you will encounter in this chapter. Okay, so now we're going to get into the interesting exercise of balancing equations. How do we balance nuclear equations, right? And you're going to see there's some difference between balancing nuclear equations and chemical equations. The first rule of balancing nuclear equations is that we have to conserve the mass number. So what does that mean? That means that in a nuclear equation, whatever the total number of mass numbers, whatever the total mass number that you have on the left side must be equal to the total mass number on the right side of the equation, all right? So that's basically what is being stated here. The sum of protons plus neutrons in the products must be equal to the sum of protons and neutrons in the reactants. And here's an example, which we're going to meet again later on. Here's an example of a nuclear equation. So as you can see, we have all the isotopic symbols for the different particles involved. And if you look at this closely, you'll see that when you add up the total mass numbers on the left side, the 235 plus the 1, which gives you 236, that would be equal to the total mass numbers of all the products, the 138 plus 96 plus 2 times 1, and they'll both be equal to the same, all right? So that's the first rule that you need to keep in mind, all right? The second rule is that not only do we have to conserve the mass numbers, but we have to also conserve the total atomic numbers on both sides. So basically, if you go back to this example here, you'll see that the 92 plus 0, right? That will be equal to 92. And the 55 plus 37 will give you 92 plus 0. So therefore, the charges or the nuclear or the atomic numbers will also be conserved in this particular example, all right? Okay, so those are the two main things that you need to keep in mind when balancing nuclear equations. Okay, so just to give you an example of how we apply what we've just learned, to this question, it says, polonium-212 decays by alpha emission. Write the balanced nuclear equation for the decay of polonium-212. So basically, decay meaning basically that it's going to lose something. It's going to lose an alpha particle. So basically, the alpha particle, remember, is this, right? The helium-4 nucleus. So we're going to write down, starting off with the reactant, which in this case is the polonium, and we're going to write down that one of the products would be the alpha particle. So the question is, what is the other product? So we have to basically utilize the two rules that we just learned: the conservation of the atomic mass, or the mass number, and the conservation of the atomic number. So basically, let's look at the conservation of the mass number. We have a total of 212 on this side, right? And here we have 4 here for the mass number of helium. So based on the conservation of mass, we can figure out what A is, right? 212 is equal to 4 plus A. So therefore, by simple arithmetic, we can determine what A is, and A is equal to 208, right? So the mass number of the element represented by X would be 208. Then we do the same thing for the atomic numbers. We know that 84 is equal to 2 plus Z, right? So again, by simple arithmetic, we can solve for Z, and that would be equal to 82. Now, the only other thing that's left for us is to identify what X is. And that's very easy, because if we know what the atomic number is, and remember we said that each element has its own unique atomic number, all we have to do is go to the periodic table and look up the atomic number of the element that has 82 as the atomic number, and identify that element, and you see that that element is lead. So therefore, this would be the balanced equation for the alpha emission of polonium-212. And that's basically it. That's basically how you determine the balanced equation based on information given, like what you're given up here. All right? Okay, any questions about this? Any questions? Any questions? All right. So here, what is provided here is basically a side-by-side comparison between nuclear reactions and chemical reactions. And as you're going to see, there's some important differences between the two, all right? The first of which is that in the case of chemical reactions, the atoms are basically separated, or the bonds between them are broken apart, and then new bonds are formed to form the products, right? In the case of nuclear reactions, basically what you have are elements being converted from one form to another. So basically, you're converting one element into another element. And we saw that clearly in the example that we just looked at, where we converted polonium into lead, all right? The next difference between them is that in the case of chemical reactions, only electrons are involved in these reactions where you have bond breaking or making, right? However, in the case of nuclear reactions, it is the protons, neutrons, electrons, and other particles such as positrons and so on, alpha particles. These are involved in the nuclear reactions, right? So that's another important difference between nuclear reactions and chemical reactions. Now, in the case of the third difference, which is probably the most important difference in terms of, the effect on us as human beings living on this earth, the amount of energy that is released in or absorbed in a chemical reaction is relatively small, especially compared to what happens in a nuclear reaction, right? Because in the case of a nuclear reaction, the amount of energy change that occurs in these reactions is typically very large, right? And this, as I said before, can have some profound effects in several ways. For example, you can harness nuclear energy to basically make products or to supply energy to the electrical grid, as was done several years ago in Crystal River, where Duke Energy had their power plant located. They decommissioned it some years ago for whatever reason. But basically, nuclear reactions, compared to the small amount of material that is used, involves the release of tremendous amounts of energy or the absorption of tremendous amounts of energy. And we're going to get into a discussion of that later on. The fourth and final difference between chemical reactions and nuclear reactions is very interesting, actually, because if you remember, when we studied kinetics, we found out that temperature, pressure, concentration, and catalyst, these can all affect the rate of reactions, right? With respect to nuclear reactions, these reactions are not affected by those factors, right? So it doesn't matter if you heat or cool or apply pressure, it doesn't matter what you do at a catalyst, you will never affect the rate of a nuclear reaction. The rate of a nuclear reaction is simply fixed as what it is, whatever it is, all right? Okay, so that's basically the difference between chemical reactions and nuclear reactions. Okay, I'm going to take one more break and then we'll resume at 1 o'clock and then we'll call it a day after that, all right? So I'll be back shortly. All right, I am back. All right, so let's finish off the time remaining by discussing the type of reaction that is taking place in the nucleus when certain particles are leaving it. So firstly, we're going to talk about beta decay. So beta decay, if you remember the beta particle, let me write it down here because I don't think I have it on this slide by itself. The beta particle is the same thing as 0 minus 1 electron, or we can use this symbolism here. All right, so that's the beta particle. And let's see what happens to the changes in the mass of the nucleus when it loses a beta particle, I'm sorry. So we're going to start off with the carbon-14 nucleus here. And when it loses a beta particle, you'll notice that the atomic number changes from 6 to 7, right? So therefore, there's an increase in the atomic number. So basically, the carbon nucleus becomes the nitrogen nucleus, all right? The mass number remains the same. There's no change in the mass number, all right? So another example here, if you do the same thing with potassium, again, you see there's an increase in the atomic number, but no change in the mass number. And this is what happens in every case where there is a beta particle that is emitted by a nucleus. Now, what actually happens in the nucleus when a beta particle is lost is that a neutron in the nucleus is converted to a proton and the beta particle. The proton remains in the nucleus, but the beta particle leaves, all right? So basically, as a result of that, the number of neutrons will decrease by 1 because you have a neutron being converted to a proton. And also, the number of protons will increase by 1 as well, all right? So that's basically what happens in the nucleus when a beta particle is lost from the nucleus. Now, let's look at what happens in the case of a positron decay. Now, remember, a positron is, let me do this here. A positron, just to remind you of what it is the same thing as 0, 1e or 0, 1 beta, all right? So it's basically considered to be the opposite of a beta particle. So let's see what happens oh, yes.
What is that last symbol, that V with a line over it?
Oh,
what does that stand for?
That's a Greek letter, beta. Let me write it down.
The V with a line over it?
Oh,
next
my
to the
bad.
beta?
Oh, right. Okay, my bad. Okay, so this here basically represents that energy is produced as well. And that is usually in the form of what we call gamma radiation. We're going to talk about that later on, but I'm glad you asked that question. And I must apologize for glossing over that. Yes, so basically what this is saying is that radiation is produced. You know, radiation that you'd have met before in General Chemistry 1, you know, in the form of, well, I don't think this is in the region of the visible range, but some form of radiation, usually it's gamma radiation. Same thing is true here, all right? Okay, so, and that is produced also here as well when a neutron is converted to a proton with the loss of a beta particle. Okay, so as I was saying before, the positron can be represented by those two symbols here and here. And what actually happens to the nucleus when you lose a positron? Well, as you can see from this example right here, the atomic number is reduced by 1, but the mass number remains the same. And that's because, of course, to balance this would have to be +1 and this would have to be 0, all right? Another example here is where you're converting potassium 38 to argon 38. Again, the atomic number is reduced by 1, while the mass number remains the same, all right? Now, what actually happens in the nucleus is that in the nucleus, a proton in the nucleus is converted to a neutron and the positron, right? So the neutron remains in the nucleus while the positron is emitted from the nucleus, and that's why we have them produced here. And again, radiation of some form would be produced as well. All right. Okay, so that's what happens in the case of beta decay. That's what happens in the case of positron decay. Oh, and by the way, in terms of the changes in the nucleus, the number of neutrons will increase by 1 because now you're making a neutron from a proton, and the number of protons will decrease by 1. So this is kind of the reverse of what we saw in the case of beta decay. Okay, as far as the different forms of radiation is concerned, they're considered to have no mass and no atomic number. All right, so that's basically as far as the positron decay is concerned. Okay, then we're going to look at electron capture, right? And the term decay is not really accurate in this case, but we'll go with it for the time being. In terms of electron capture, what is happening is that the particular nucleus will basically react with a beta particle and capture it, and then you're going to have the resulting changes in the nucleus, which results in the formation of a new nucleus, all right? So in this particular case, what you'll notice is the atomic number is reduced by 1 while the mass number remains the same. That is true in this example, that is true in this example. And what actually happens in this case is that the beta particle that is captured is going to react with a proton, and you're going to end up with a neutron as a result, all right? So as a result of that, the number of neutrons will increase by 1, as you can see here, and the number of protons will decrease by 1, all right? So that's what happens in the case of electron decay. And then in the case of alpha decay, we saw this example earlier, and you can clearly see that there will be significant changes in the nucleus, especially with respect to the composition. As you can see here, the atomic number is decreased by 2, and the mass number is decreased by 4, right? Now, as a result of that, we can conclude that the number of neutrons will decrease by 2, and the number of protons will decrease by 2, resulting in the formation of the new nucleus. And then we have what is known as spontaneous fission, where basically a nucleus will undergo a spontaneous change to form other particles such as a neutron and maybe some other nucleus, all right? So that is seen in this example right here, all right? So these are just the different types of radioactive decay reactions that can take place. Now, this begs the question, can we actually predict whether or not a particular nucleus will undergo a particular type of radioactive decay? And the answer is that it depends, or, you know, to a certain degree, you can do so. Now, how do we make that prediction? Well, we can look at the ratio of the number of protons to the number of neutrons. And what you're looking at here is that there's a plot of the number of neutrons on the y-axis and the number of protons on the x-axis. Now, this pink line here, this, or black line, is it pink or black? Can't tell from here, but this solid line here basically represents where you have the ratio of the neutrons to protons being equal to 1. And what you'll find, and also let me just say that these dots right here represents the different nuclei that are considered to be stable. In other words, they will not react in one way or the other to form a new nuclei, right? So what was found was that at about atomic number 20, where the atomic number or the number of protons is 20, you'll find that the stable nuclei will fall on that line where the ratio of neutrons to protons will be equal to 1. But as the number of protons and neutrons increases, what you'll find is that that ratio becomes greater than 1, right? We call this here the belt of stability. This is basically the region where the nuclei that are found in that region will be stable and therefore will not undergo any reaction or any nuclear reaction, all right? Now, it says here that above the belt of stability, what will happen is that the nuclei will undergo beta emission so that the ratio will fall within this band here, where, or the belt of stability here, right? So basically, if the nucleus falls within this region here, what that means is that the neutron to proton ratio is too large, and therefore beta decay will reduce that ratio so that the neutron will fall closer to the belt of stability, right? And then if you have any nuclei which is below the belt of stability, in other words, if the neutron to proton ratio is too small, then position decay or electron capture would be the type of reaction that these nuclei will undergo in order to achieve a structure which is closer to the belt of stability, all right? Okay, one more thing and then we're going to call it a day. Certain numbers of neutrons and protons are extra stable, and these are the numbers right here. You don't need to memorize them, but you need to know that, you know, there's some stability associated with nuclei, which has certain numbers of protons and neutrons, right? Kind of similar to the numbers of electrons, which correspond to stable atoms, and more particular noble gases, all right? And then it says here, nuclei with even numbers of both protons and neutrons tend to be more stable than those with odd numbers of neutrons and protons. That's just another trend that is observed. We won't go into the reasons why that is so. That is just something that, you know, that has been discovered by nuclear scientists. And then this one, which I would say you need to know, all isotopes of the elements with atomic number higher than 83 are radioactive. In other words, elements whose atomic numbers are greater than 83 are unstable and therefore will undergo some sort of nuclear reaction to form a more stable nucleus, all right? And then this here is basically a table which summarizes, you know, some of the features of stable isotopes, all right? Okay, we're gonna stop here for today. And then what I'm gonna do is publish the videos for this chapter as soon as I get off here. Make sure you watch the videos, and of course, come with any questions you may have. I'm here to answer them, and then we'll look at some problems, all right? Okay, so that's it for today, folks. I'll see you guys on Monday, all right? And I'll be available, by the way, for office hours on Friday from 2 to 5 if you have any questions. All right, take care.